All right, we're going to continue section 13.9 in this video, and we'll do a couple of exercises from the textbooks. Page 890. We're going to do number 12, which says in exercises 11 through 14, find the extreme values of f in the region described by the given inequalities. In each case, assume that the extreme values exist. And so for 12, they give us our function is f of xy equals x cubed plus x squared plus y squared over 3. And the region that they give us is x squared plus y squared is less than or equal to 36. So R equals this set of points xy such that x squared plus y squared is less than or equal to 36. All right, so we did a problem like this in section 13.8. So now we're going to see how the difference in doing the two types of problems in 13.8 and 13.9. So the first part of the problem is done the same in both sections. So first, you don't have to sketch your region usually, but I'm just going to sketch it to make sure we understand what's going on here. And actually the problem we did in 13.8 just so happened to be the same region as the region in this problem. In the so our region here is a circle, a disk with radius 6. So I did assign, well not assign, but I gave you all in the set of practice problems a problem like this as well, where the region is not a disk. So you can see how it differs. That problem is the one where it's not a disk. It's slightly different from when we have a disk, where this has radius 6. All right, so that's the region we're considering. Now the boundary of that is x squared plus y squared equals 36, not 6, equals 36. And we're gonna use Lagrange multipliers on the boundary, but we have to handle the points that are inside of the circle first. So we don't have to do them first, but we'll handle those first, and then we'll use Lagrange multiplier on the boundary itself. So now in finding extreme values inside of here, we're just going to take the partial of f with respect to x and y, find our critical values, and then we're going to look at which critical values actually lie inside of there. If they don't lie inside of this disk, then we're not concerned about them. So first, our partial of f with respect to x is 3x squared plus 2x, and our partial of f with respect to y is 2/3 y. All right, so setting these both equal to 0, we get here, that's x times 3x plus 2 equals 0, and over here this is just 2/3 y equals 0. So here we get x equals 0. Now remember, they both need to be 0 simultaneously, but there are no y's in here, no x's in there, so we can just solve. So this says x equals 0, or x equals negative 2/3. In this, we just get that y equals 0. So now what we do is we take every combination of x and y that we can get from here, and that will give us our critical points. So if x is 0 and y is 0, then both of these equations are 0, so that's one of our points. If x is negative 2/3 and y is 0, then both of these equations are 0, so that's also a critical point for us. So negative 2/3, comma, 0. Now, are these points inside of here? Yes, both of those points are inside of there. So if one of them wasn't inside, we wouldn't consider that point. So we're going to go through, we have these points, we're going to go through and find points on the boundary we need to consider. And then we're going to look at however many points we have, we're going to substitute them all into the function and see what are the largest and smallest values we get when we substitute in the function are. So We don't want to forget about these. So it may be useful to substitute them in the F now, or you can wait and do it all at the end. I tend to just do it all at the end and just try to keep in mind I have to go back to these points. So now we'll address the boundary, and we're going to use Lagrange multipliers to do that. So boundary of R using Lagrange multipliers. And it would be good practice to, after we've done this using Lagrange multipliers, to try to do this boundary approach using 13.8. So what we're about to do here, instead of doing it with the 13.9 approach, use the 13.8 approach. So for Lagrange multipliers, we have the gradient of f equals lambda times the gradient of g, where our g is x squared plus y squared. So let's go up so we can see what we're doing. Oh, so we have the gradient for f already here, and then the gradient for g. This x squared plus y squared is our g. So our three equations, the first one, oops, so let me put that on the right as I normally do. So f sub x is 3x squared plus 2x equals lambda times g sub x is just 2x. That's our first equation. And then f sub y is 2/3 y equals lambda times 2y. So 2/3 y equals lambda times 2y. It's our second equation. And don't forget about your constraint equation, which is for us x squared plus y squared equals 36. All right, so those are our three equations we're going to use. All right, and you start wherever you want. Usually, you can't start with your constraint, but you can start with whichever one of these two you want to start with. I tend to go for the simplest one, which is number 2. So I'm going to start with that. So 2 gives us that 2/3 y equals lambda times 2y. I'm going to multiply both sides by 3 first off, just to get rid of the fraction. So that gives us 2y equals lambda times 6y. And moving everything over to the left gives us that 2y minus 6y times lambda equals 0. And we can factor out a 2y from all of this. So 2y times 1 minus 3 lambda equals 0. And that tells us y equals 0. Or here, that's 1 equals 3 times lambda, or lambda equals 1/3. All right, so we have two different cases to consider in using 2. So first off, I'm going to consider y equals 0, and then I'll go to the lambda equals 1/3 case. So, oops, I don't want to do that up there though. I'm going to go to the next page because I actually want to work over here, and I'm out of space. All right, so I'm going to just stay to the right because of where we were working before, and just try to keep things in order. So now we're looking at y equals 0, and whenever we're looking at different cases, I just underline that. So for y equals 0, we can take this, and we got this from equation 2, so we can't put it back into equation 2. Then equation 1 doesn't have any y's in it at all, so our only option is equation 3. So we'll take this and put it in equation 3. And when we put that in equation 3, we end up just getting that, what was equation 3? We end up getting x equals plus or minus 6. So now notice we've exhausted everything for equation 2 with the y equals 0 because there are no y's in it. Sorry, was that equation 2? Yeah, there are no y's in equation 1. So we have 2 points now, 6, 0 and negative 6, 0. So 2 more points. So 6, 0, negative 6, 0. And we already have 2 points from earlier. We were looking inside of our region. All right, so now we still are under equation 2, but we had another case to consider. We had the case to consider when lambda was equal to 1/3. So lambda equals 1/3. There are no lambdas in equation 3 because that was just our constraint equation. So we're looking at equation 1, sorry. We're gonna put this in equation 1. We got it from equation 2, so we can't put it back in there. So now we put this in equation 1. We end up with, what is our equation 1? Sorry, let me find it. Our equation 1 was 3x squared plus 2x equals lambda times 2x. So we end up with 3x squared plus 2x equals 2/3 x. Yes, 2/3 x. So now if we take this and we solve this for x, so this is the same as 3x squared, and then we have 6/3 minus 2/3, so plus 4/3 x equals 0. And then we can factor out an x from both of these terms. And we end up with x times 3x plus 4/3 equals 0, which tells us that x equals 0, or so that's x equals 0, or 3x equals negative 4/3. And this is just x equals negative 4/9. All right, so now from that, we still don't have actual points because that y equals 0 was, we've already finished with that. So remember when I underlined stuff, those are two separate cases entirely. So we're not, this is not go, these don't go with that y right there. We have to find the y's that correspond to this. So in doing that, we're going to have to use our constraint equation, which is equation 3. Which was x squared plus y squared equals 36. So when we put these in there, so first let's deal with x equals 0, sorry. So dealing with x equals 0, put that into our constraint equation, and we end up with y equals plus or minus 6. So now we have the 2 more points, which are 0, 6, 0, negative 6. And then we're going to deal with x equals negative 4/9. We're going to put that into 3. And when we do that, we are going to get, we're going to square this. So we're going to get 16/81. So actually, let's do it this way. We're looking for y. So y squared equals 36 minus 16/81, which is whatever 36 times 81 is, minus 16 all over 81. And of course, on your test, I wouldn't give you a problem where the numbers were like this. What is 36 times 81? All right, so we're going to get 2916 minus 16. So we're going to get 2900/81. 2900/81. So now that was y squared. So y is going to be equal to plus or minus the square root of this. So y equals plus or minus. On the denominator, we're going to get 9. The numerator, 29 times 100. So we're going to get 10 times the square root of 29 over 9. So now we have 2 more points. I'm going to put these points on the next page. So there's negative 4 over 9, and then 10 root 29 over 9, and negative 4 over 9, negative 10 root 29 over 9. All right, so we have negative 4 over 9, comma, 10 times the square root of 29 over 9, and then negative 4 over 9, comma, negative 10 times the square root of 29 over 9. All right, so this last part, the last step that we have is to compare. So we'll compare the values of, let's see, f, let me go in order. First points we found were 0, 0, f of negative 2/3, 0. Those are the points that we found inside of the region. And the points that we found on the boundary were f of, let's see, what was the first point we found? 6, 0 and negative 6, 0. 6, 0, f of negative 6, 0. Then we found 0, 6 and 0, negative 6. F of 0, 6. F of 0, negative 6. And then lastly were these 2 points. F of negative 4 over 9, comma, 10 root 29 over 9. And f of negative 4 over 9, comma, negative 10 root 29 over 9. And given our function for this problem, you certainly would, well, these first points would be fairly easy to do. Those certainly will probably want to use a calculator for these four, or actually they're not too bad, but you would go through, you can we'll put these in a calculator and see where you get the largest value and where you get the smallest value and what they ask for each. Find the extreme values of f in the region described by the given inequality. So the extreme values would be whatever number you get that's the largest, the biggest number will be an extreme value, and whatever number you get that's the smallest would be an extreme value. Nothing else that you get out here would be an extreme value. All right, so we'll stop this video here and then we'll do another example from section 13.9 in the next video. And you can try this one. So these points you would get the exact same way whether you're doing 13.8 or 13.9. You can try the last part, the Lagrange multiplier part, to get these using the 13.8 approach. And for this problem, because of the steps in our algebra, I'm guessing the 13.8 approach actually would be faster for these than it was in 13.9.